Here is the question that I asked at the end of the last part of this lecture. So the way we get this force is we use the equation that we just found and recognize that that is just a slope. So in the vicinity of x equals 3.5 meters, we have a straight line, and so we can just do a rise over run and get that slope. And when you do that, and remembering the negative sign in the equation, you have a slope of 2 and that negative sign, and it had better be in newtons, and so the answer is E. The last thing I'm going to do in this unit is power. Power is defined as the rate of energy conversion or transfer, and so this delta E here is an amount of energy that is either converted or transferred. So power often has a somewhat vague meaning because that delta E can mean any of several things. That delta T, of course, is the time interval over which the conversion or transfer takes place. And because this is over a finite amount of time, delta T, this is then an average power. If we want an instantaneous power, then as usual, we'll need to take a limit as the time interval goes to 0. Suppose that delta E actually is a change in system energy, which is what we usually mean by delta E. Then it's equal to the work done on the system, which in a simple case could be a force, an external force, times the displacement. In that case, now our average power looks like this, and the delta x over delta t is just the average velocity. So that's a fairly useful common expression that can get you the power if you just know the force acting on an object and the velocity that the object is moving at. And of course, again, you can take a limit as delta t goes to 0 to get an instantaneous power when both the force and the velocity are changing. As usual, we can get the units for power just from a defining equation. And so we have that an energy is in joules, and a time is in seconds, and so a power must be in joules per second. And we define that as watts. And one thing to be very careful about is that the symbol W for watts is of course the same as the symbol W for work, and so you need to be careful not to mix up the symbols that you're using for units with the symbols that you're using to represent quantities. Let's look at an example with power. So suppose we have an elevator, which with a few people in it is 400 kilograms, and it's being raised by a cable, which is on a motor. And we want the elevator to be able to go up 10 stories, which would be about 30 meters, in 15 seconds. What power output do we need the motor to have? So when the elevator is going up at a constant speed, its acceleration is 0, and so we know at that point that the force that the cable is exerting on it is equal in magnitude to the gravitational force, and that will be in turn the force that the motor is exerting on the cable. We can do an energy analysis. If our system is the elevator and the Earth, then as the elevator goes up, there's a positive change in potential energy. And that's it. It's going up at constant speed, and so the kinetic energy doesn't change. And so that change in potential energy has to come from work done. And the only external thing that can be doing that work is the motor. And so we see that in raising the elevator by 30 stories, we will have that the work done by the motor equals the change in the gravitational energy of the elevator, which is just going to be mg delta y. And we can get straight to what we actually want, which is the power of the motor then, if we simply say it will be the work of the motor divided by delta t, and so that's just mg delta y over delta t.